again, this video is for the second half of section 2.1. It's the second video of chapter 2 in anatomy and physiology. First of all, I need to confess that I made a goof in making the last video. I forgot to advance the slides after we talked about the different models of the electron, and I neglected to talk about radioactivity. So we're going to start with that. It doesn't change the order of anything. It just makes the last video a bit shorter and this one a tiny bit longer. Then we're going to move on and talk about ions, electrolytes, and free radicals, and we're going to finish up by reviewing chemical bonds, something that I hope you saw in either high school or college chemistry already. So isotopes are an element where the atoms have a different number of neutrons. Okay, so let's imagine, first of all, a carbon atom that has 6 protons, 6 electrons, and 6 neutrons. Okay, so its atomic number, the number of protons, is 6. Its atomic mass, the number of protons plus neutrons, is going to be 12, because each one of those, 6 protons and 6 neutrons, has an atomic mass of 1. It's going to be neutral because our positive protons and our negative electrons balance each other out perfectly. Okay, so that's our carbon atom. Now let's imagine a second carbon atom that has 6 protons, 7 neutrons, and 6 electrons. Okay, so its atomic number is still the same. It's still carbon. It still has 6 protons. It's still electrically neutral. The positive protons are still in balance with the negative electrons. What's different is its atomic mass or its atomic weight. Okay, we use those terms interchangeably. Atomic mass is slightly more scientifically correct. Okay, because now we have 6 protons with an atomic mass of 6 plus 7 neutrons. Each of those are 1 atomic mass unit heavy. So 6 plus 7 gives us 13 atomic mass units as the mass of that atom. So these two carbon atoms, our first one compared to the second one, are isotopes of each other. They have a different number of neutrons. They're still the same elements. In some ways, their chemistry will be the same, and in other ways, the chemistry will be different. So here's another example. This is hydrogen. So we have our hydrogen over here. It has 1 proton and 1 electron. Here we have the same 1 proton and 1 electron, but here we also have a neutron in the nucleus. Okay, so here our atomic mass was 1. Remember that electrons are so tiny, we don't include them in that calculation. Here, our atomic mass is 2, because each one of these has a mass of 1 atomic mass unit, and we don't count electrons because they're too small. And our third isotope over here has 1, 2, 3 subatomic particles in the nucleus, so its atomic mass overall for the atom is 3 atomic mass units. And here we have the 2 neutrons and 1 proton. So in some ways, all 3 of these are going to be chemically similar, but these 2 or 1 extra neutron do have some impacts on the properties of the hydrogen. Radioisotopes are things that give off radiation as they decay. So if something is unstable, they typically make changes to themselves, and this isn't a conscious thing, this is a chemistry thing, but they make changes to themselves to gain greater stability. So radioisotopes undergo a process called decay that help them become more stable, and in the process of this decay, they give off radiation. And this radiation can be pretty intense. It can cause changes to DNA, which we call mutations, and those mutations can cause cancer. Okay, so examples of radiation that we encounter are UV radiation and X-rays. Okay, this is why if you ever get an X-ray, they drape your body with a lead vest. The X-rays can't get through the dense lead vest. This is why we really want you to wear sunscreen when you go outside. So the ionizing radiation from the sun doesn't damage your skin. We also have alpha, beta, and gamma radiation. There's this concept called a half-life, and a half-life is the time it takes for half of the thing to either become stable or to clear the body, to leave the body. Okay, so those are definitions there that are important for you. Right now, the United States sets the standard for normal acceptable exposure to radiation at 50 millisieverts per year. Okay, so there are things that we do to protect ourselves from not getting too much radiation. The sunscreen is a big part of that. Minimizing x-rays that aren't essential is a big part of that. We do have sources of radiation that we encounter every day. TVs give off a very small amount of radiation. Cell phones give off a very small amount of radiation. We also have background radiation. Soils and the bedrock in some places release a gas called radon, which contributes to the radioactivity that we're exposed to. Marie Curie is one of my heroes. She was the first woman in the entire world to receive a PhD. She also was the first woman to receive a Nobel Prize. She's the one who came up with this term radioactivity. And she studied radioactivity, discovered 2 elements on the periodic table, worked with how to use radiation as a treatment, did a lot of really, really incredible stuff. She was a very driven, very passionate person about science and about her field. They also didn't know about some of the dangers of radiation, and she died of radiation poisoning as a result of all her work with things that gave off radiation. She died at the age of 67. Okay, so now we're moving into our next objective. So we have some definitions here. I'll let you read them. Everybody can do that. I have a little memory trick for telling the difference between an anion and a cation. So I'll share it with you, and if it helps you, great. And if it doesn't help you, just put it out of your mind. Not essential. Okay, so cations lose an electron and have a positive charge. So when I am trying to remember this, I think of a cat, think of a cute little kitten, and it's got that paw with the little toe beans on it, right? So it's paw positive, and the cation is the one that's positive. So that's my little memory trick. If it helps you, wonderful. As we get into talking about ions and how they're formed, I like to use a picture to do that. Okay, so sodium. Sodium on its own, elemental sodium, not bonded with anything, is an explosive metal. It's silvery in color. It's not super shiny, but it's not super dull, kind of brittle. But when elemental sodium touches water, it explodes. There's some really cool videos on YouTube. I strongly recommend you check them out. So, sodium has usually 11 protons. That's what makes it sodium. 11 electrons to balance out those protons. And then it also has 12 neutrons typically with the protons in the nucleus. So my protons and my neutrons are here. And then I have 11 electrons. Okay, so in our first shell, we have 1 and 2 electrons. In the second shell, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I've counted 10 electrons so far. And then I have this one more electron up here. So one thing that's important to note is the number of electrons in these first 2 shells, really first 3 shells, are fixed. Okay, you are always going to find 2 electrons in the first shell if it's full, 8 electrons in the second shell if it's full, and 8 electrons in the third shell if it's full. And atoms really, really want to have full valence electrons. Okay? It's these valence electrons in the outside ring or the outside shell that do chemical reactions. And atoms don't really want to be always doing chemical reactions. Okay? They would rather either be stable on their own or be stable with another atom or group of atoms and then just stay there. Okay, so this sodium, elemental sodium by itself, has 1 electron in the outer shell. And it's really reactive because of that 1 electron. That 1 electron right there, it don't want it. It doesn't want just 1 electron in that valence shell. That's what makes it react so strongly with water. Okay, so let's go over here and look at chlorine. Chlorine is a poisonous green gas. It kills lots of things very easily. It's why we put it in swimming pools. It's why we put it in drinking water to get rid of the microbes that could be living there and could make us sick. So chlorine is a little bit bigger. It's got 17 protons, balances those out with 17 electrons. And then in the nucleus, along with the protons, are 18 neutrons. Okay, so our nucleus is here with our protons and our neutrons. And our first shell has 1, 2 electrons. Second shell has 1, 2, 3, 4, 5, 6, 7, 8, exactly like we'd expect to see. And then our outer shell here, which would have 8 electrons in it if it were full, has 1, 2, 3, 4, 5, 6, 7, and it doesn't have an 8th, okay? Because 17 electrons, I've got 2 in the first, 8 in the second, that gives me 10, and then I have just 7 in this outside one, which is so close to being full, but not quite there. And that's what makes chlorine so reactive. So, what these two atoms really want to do when they come in contact with each other is for the sodium to give up this electron and transfer it to this chlorine. And if that happens, here we have lost an electron. So now we have 11 protons and 10 electrons. Okay, keep in mind our protons didn't change. This is still sodium. Our electrons changed. We went from 11 to 10 as that outside electron was given away. So now we have 1 extra positive charge compared to the negative electrons. So we can say this is a positive ion. Over here, where the chlorine got the electron, now we have a full outer shell. We have an 8th electron in that outer shell. So we have 17 protons. It's still chlorine. But now we have 18 electrons. We have an extra negative charge here. So we have 1 more negative charge than we have positive charge. We say this is a negative ion. So electrolytes are things that ionize in water. They're able to separate like this into charged ions. Okay, so electrolytes include potassium and magnesium. Sodium and chloride are 2 of them. When you hear that Gatorade or Powerade have electrolytes in them, this is what they're talking about. We need to keep our electrolytes in balance. We want to have them in our body because they regulate a lot of different things, especially nerve impulse and muscle contractions. So the next thing we need to talk about are free radicals. Free radicals can be made naturally as a result of metabolizing your food. They can come from radiation exposure, such as being in the sun too long and getting too much radiation. They can also come from certain medicines and certain chemicals that we can be exposed to, for instance, at our jobs. So free radicals have a weird number of electrons. Remember that I told you that atoms typically have 2 electrons in the first shell, 8 in the second shell, 8 in the third shell. Free radicals can be the exception to that rule. They can do some funky things with their valence electrons, and these can be really damaging to cells. Okay, we want to minimize free radicals in our cells, and one way that we do that is antioxidants. So antioxidants are chemicals that neutralize free radicals. One of the ones that's critically important in our body that we don't need to do anything about to get it to run is superoxide dismutase, or SOD is our fancy abbreviation for it. In your cells, SOD is an enzyme that's always working to neutralize free radicals. Other ways that we can help out with this, we can eat a diet that has lots of vitamin C, carotenoids, those are vitamin A's, so you're going to find those in things like carrots and sweet potatoes. And then vitamin E and selenium also have antioxidant properties. So now we're going to move into the chemical bonding portion. Okay, so there's some kind of complex stuff here. My hope is that you guys have seen this before. If you haven't seen this before and you're feeling super confused about something, please send me an email and let me know so we can talk through any questions that you have. Okay, so when we have any 2 or 3 or more atoms that come together with any sort of chemical bond, that's a molecule. When they are 2 or more different elements, then we have a compound. Okay, so the difference between a molecule and a compound is pretty subtle. Take some time to play with that. Make sure you have that in your head. The molecular formula tells what elements and how many of each element are in the molecule. And then we have the structural formula that gives us some information about where in the molecule they're located. And isomers we're going to talk about on the next page. We kind of need a picture in order to see those. It's things with the same chemical formulas, same molecular formulas, but the atoms are arranged differently. We'll look at a picture of it. All right, so this is where it starts to get interesting. If we look over here, I'm going to work from right to left on this one for demonstrating some things. So over here, we have 2 things with the same molecular formula. I have C2H6O, C2H6O. So what this tells me is I have 2 carbons, 6 hydrogens, and 1 oxygen. 2 carbons, 6 hydrogens, 1 oxygen. This doesn't tell me anything about how those atoms are arranged. I don't have any information about that. So our condensed structural formula gives us some information. Okay, so this is like reading words. I have a CH3. That CH3 is connected to a CH2, and that CH2 is connected to an OH. Here it's a little different. I have a CH3 connected to an O connected to a CH3. Okay, so we can see in picture form how different these things really are. So here's my CH3 connected to my CH2 connected to my OH. Down here, here's my CH3 connected to my O connected to my CH3. So these are very similar structures, but they are not the same. And they are very different in their properties. Ethanol. We have up to 10% ethanol added to our gasoline. Ethanol is also the thing in alcohol that you drink that your body metabolizes and makes you intoxicated. Ethyl ether cannot go in your car and cannot go in your body. So these are very different things. Molecular weight is an important concept. again, I hope you guys saw this in either high school chemistry or earlier in your college chemistry career. What we're going to do here is we're going to find out the number of atoms that something has multiplied by the atomic mass of one atom of that type, and then add all of those up. So this is kind of a classic example. If we're talking about glucose, we have 6 carbons, 12 hydrogens, and 6 oxygens. I have 6 carbon atoms. They each weigh 12 atomic mass units. 6 times 12 gives me 72. I have 12 hydrogen atoms. Each one of those hydrogens weighs 1 atomic mass unit, so we have 12 atomic mass units from the hydrogen. And we have 6 oxygens in my glucose. Each one of those weighs 16 atomic mass units, so 6 times 16 is 96. Altogether, the molecular weight of glucose is 180 atomic mass units. All right, and finally, we're moving into chemical bonds. Okay, so we're going to talk about ionic first. This is what we looked at earlier with our sodium and our chloride. So remember that sodium on its own, super reactive, has that one extra electron that's hanging out in the outer shell. Chlorine is super reactive because it has one electron missing from its outer shell. So we take the explosive metal and the poisonous gas and we put them together and we get sodium chloride, which is absolutely delicious on our French fries, and we also need in large quantities in order to survive. Chemistry is wonderful. Okay, so in a chemical bond, we have an anion, the thing that becomes negatively charged, attracted to a cation, the thing that is positively charged, after electrons move from one to the other. So this association is easily broken by water because water is a polar molecule and likes to interact with both positive and negative things. Covalent bonds are when electrons are shared. Okay, so here we have one hydrogen atom and a second hydrogen atom. They each have one electron in the outer shell. That first shell likes to have 2 electrons in it. Having 1 makes it unstable. So they join up. So this electron, for instance, maybe came from this atom. This electron maybe came from this atom. And they're sharing them. And as they share, this guy can now claim 2 electrons. This guy can also claim 2 electrons. And as long as they stick together, they're happy and unreactive. Guys, I want to make a point here. I have a habit of saying that atoms are happy. Just to be clear, atoms don't have any sort of personality. When I say happy, I mean unreactive. We can also have double covalent bonds. So carbon dioxide makes up a significant portion of our atmosphere. It's what you breathe out as a byproduct of respiration, and it involves 2 double covalent bonds. So we have our oxygen over here. Oxygen has 1, 2, 3, 4, 5, 6 electrons of its own in its outer shell, and then it claims 2 more. I lost my pointer. It claims 2 more from the carbon, and now both the oxygen and the carbon, when we look at these here, are considering all of theirs their own. Okay, so our oxygen is thinking, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons, even though only 6 of them came from the oxygen originally. This oxygen over here is doing the same thing. It had 6 electrons, and then it's sharing 2 more with the carbon, so the accounting that this oxygen is doing, it's thinking it has access to all 8 of these electrons now, so it's also stable. The carbon in the middle had only 4 electrons. Okay, so maybe these 2 and these 2. And carbon is fairly non-reactive on its own. It doesn't do anything explosive. It doesn't do anything deadly on its own as elemental carbon. But it is more stable when it's sharing 2 electrons on each side from the oxygens. So this is an example of a molecule with 2 different double bonds. Covalent bonds, where electrons are shared, can be either nonpolar or polar. So nonpolar is when the electrons are shared evenly, and polar is when the electrons are shared unevenly. So I want to give you kind of an analogy for a polar bond. Okay, so I want you to imagine you have a little brother or little sister and or little cousin, whoever you want to imagine, and somebody made brownies, like homemade, delicious, chocolate goodness brownies. And there's one left in the pan. And you're about to take it because you're the older kid in the situation, and your brother, sister, they're younger and littler than you. You are going to have this brownie. And just before you take your first bite, your mom or your dad, your grandparent yells at you that you have to share with the little kid. Well, you're older and bigger and stronger, so what do? You cut it in half, and then you real quick take the bigger half and walk away, right? So you're sharing. You did what you were told to, but the sharing may not be exactly equal. Okay, so here are some visuals of this. If we have a carbon-carbon bond, carbon and carbon are equal in all of their properties, and so they're going to share the electrons equally. Here we have a hydrogen and a water, and the property that makes atoms want to hold on to electrons more closely is called electronegativity, but we're not going to get into that right now. So over here, the electron, because of its chemical properties, it's the bigger and the stronger guy. It's like you in the brownie analogy. It's going to take more of the electrons because it feels like it. It's bigger, it's stronger, and it can. And again, I'm giving human characteristics to atoms. They don't actually consciously think these things. I'm sure you guys know that. But as our oxygen over here, I lost my place here. As the oxygen holds on to those electrons more tightly, electrons have a negative charge, this area of the molecule is going to have a partial negative charge. It's not a full negative charge like we saw with our chloride when the electron was fully transferred. Over here, the hydrogen, with its lower electronegativity, is less able to hold on to the electrons. So the electrons are going to tend to be over here. Electrons are negative. So over here, we're going to have a partial positive charge. Okay, so this is a polar covalent bond. The atom has 2 poles. It has a positive pole and a negative pole. The electrons are not being transferred completely, but the electrons do tend to hang out in one place as opposed to another place. All right, hydrogen bonds are super important. Hydrogen bonds are a characteristic of water and give water all of the weird properties that it has, like surface tension, cohesion, adhesion. So let's look at a water molecule. So I'm going to start with this water molecule right here. So I have an oxygen and 2 hydrogens. And this is a polar molecule like we were just talking about. The oxygen has electrons, each of the hydrogens have electrons, but because of water's extra or higher electronegativity, the electrons tend to hang out with the oxygen. And so the oxygen tends to have a partial negative charge, and the hydrogens tend to have a partial positive charge. Okay, so between the oxygen and the hydrogen are covalent bonds. Between the oxygen and the hydrogen, the way water forms is a covalent bond. Then, when you put lots of waters together, the partial positive side of one water molecule wants to hang out close to the partial negative side of another water molecule. And between them, where we have the partial positive tending to be close to the partial negative, we form something called a hydrogen bond. And this hydrogen bond is the thing that gives water all of its properties. Okay, so super important. I would expect to see this on an exam because I think this is really important. The thing that holds the oxygen to the hydrogens in a water molecule is a covalent bond. The thing that gives water its properties, that allows interaction between one water molecule and the next water molecule, is a hydrogen bond. If you have any questions at all about that, please send me an email and let me know. Or come to office hours and we'll talk about it. All right. Finally, we have something called van der Waals forces. These are weak and short forces where the electron density changes, and for just a second, the atom has the property of polarity. They are very weak. They're much weaker than a covalent bond, but when there are lots of them happening all together, they can influence things in physiology. And that's the end for chemical bonding. Guys, this stuff is really important, so if you do have any questions at all, please send me an email or come to office hours so we can talk through any confusion that you have.